Look at the sheer footprint of a modern utility-scale solar array. We are deploying gigawatts of power across thousands of acres of terrain. But for the engineering, procurement, and construction firms building these sites, the physical hardware is no longer the primary friction point. Getting steel in the ground is a solved problem. The actual bottleneck, choking deployment, happens long before a single panel is mounted. It is the data environment. Information is heavily fragmented across isolated departments. This diagram illustrates the standard workflow for most firms. Engineers draft physical layouts in standalone CAD programs, finance builds pricing models in disconnected Excel spreadsheets, and sales teams track clients in isolated CRM pipelines. Moving project parameters between these isolated software silos requires manual human intervention. Engineers must export layout metrics so analysts can rebuild the exact same project in a financial model, introducing severe latency into the process. When a client requests a minor layout adjustment, that manual transfer has to happen all over again. This inevitably introduces compounding version control errors between what the engineers design and what the sales team actually quotes. Software fragmentation actively bleeds project ROI and increases overhead before construction even begins. The alternative to this fragmented workflow is a single source of truth database architecture. Nexergy's solar AI platform provides a clear example of this centralized infrastructure in practice. The platform unifies engineering design, automated financial modeling, and lifecycle project tracking into one continuous data pipeline. Centralizing these functions yields measurable outcomes. By running the engineering layout directly inside the same environment as the financial tools, firms reduce their system design time by up to 70%. Because the financial models pull directly from the raw engineering outputs without human transcription, the resulting yield models achieve 99% calculation accuracy. A unified digital infrastructure is a strict requirement to eliminate operational friction and remain competitive in the market. To understand how this unified environment works, we have to examine the software stack from first principles, starting at the foundation. This diagram outlines the architecture of the platform. The bottom tier is the context-aware engineering engine. A standard one-size-fits-all mathematical model cannot accurately calculate energy yields across diverse physical topographies. A commercial warehouse roof behaves differently than an agricultural plot. The engine is built to dynamically switch between 4 distinct calculation modes: commercial rooftop, floating solar, ground-mounted farms, and agrivoltaic systems. Once the topography is set, the engine ingests precise environmental inputs. It pulls localized solar irradiance data to calculate exactly how much raw sunlight will hit that specific geographic coordinate. It also integrates localized environmental standards, incorporating TGO emission factors to establish an accurate baseline for the project's ecological impact. Using these inputs, the engine runs its primary calculations to dictate precise system sizing and determine the anticipated performance ratio, or PR. The algorithm then factors in anticipated physical system losses, such as shading, cable resistance, and inverter inefficiency, to refine the final yield model. Context-aware algorithms are strictly mandatory to translate raw environmental inputs into reliable, bankable engineering baselines.
This brings us to the critical workflow handover point, where most EPCs experience delays, converting those physical design metrics into business economics. That conversion happens here, in the second layer of the software stack, automated financial translation. The core mechanism of this layer is the Automated Bill of Quantities, or BOQ module. The BOQ instantly extracts the exact material components, from total panel counts to specific wire lengths, and labor requirements directly from the engineering layout beneath it. The platform automatically applies preset baseline costs and margin templates to these extracted quantities. This immediately generates advanced economic indicators, starting with the levelized cost of energy, which reveals exactly what each kilowatt-hour will cost over the system's lifespan. Simultaneously, it calculates the net present value and the internal rate of return based entirely on that rigorous BOQ data. All of this generated financial and engineering data then instantly populates a standardized dual-language PDF quotation, fully branded and ready for the client. Automating the financial translation layer eliminates the primary source of delay between system design and the final client proposal. The utility of a unified database extends far beyond the pre-sales and quotation phases. This leads to the final, top layer of the architecture stack, lifecycle management and AI operations. The moment a client accepts a proposal, the system instantly converts that project data into a 13-step Gantt chart framework. This framework governs ongoing procurement tracking and assigns specific tasks to construction teams during physical deployment. Once the system is deployed and active, the platform enters its post-deployment phase using AI-driven performance analytics. This graph illustrates how the platform ingests live, real-time yield data straight from the active solar array. The AI continuously compares this live operational data against the original predictive model generated by the engineering layer to flag any deviations in performance. By analyzing these precise deviations, the system triggers predictive maintenance alerts, allowing teams to address physical issues before critical hardware failures occur. Simultaneously, it tracks real-time carbon reduction metrics, compiling them for standardized ESG reporting to stakeholders. By integrating post-deployment analytics, a complete platform transforms from a static calculation tool into a dynamic operational hub. We can now view the complete three-tiered architecture stack as a single interdependent ecosystem. The ultimate operational advantage of this structure is the ripple effect inherent to a single source of truth database. If an engineer makes a single physical layout adjustment in the bottom layer, such as removing 5 panels due to a roof obstruction, that change automatically cascades upward. That single adjustment instantly updates the financial bill of quantities and recalculates the levelized cost of energy without any manual data entry required. The data continues upward, simultaneously updating the executive KPI dashboard and adjusting sales pipeline forecasts in real time. This multi-tenant architecture is built for scale. With role-based access and API connections, it serves the exact needs of solo consultants just as effectively as massive enterprise EPCs. In an industry defined by tight margins and complex deployments, a centralized data pipeline is the base-level infrastructure required for survival.